This video is a bit different from others because I don't normally lecture on this material. I just do some demonstrations and examples in class because the equations are pretty familiar by now and appear quite nicely in the textbook. For background, motion in general is a combination of two things: the translation of an object, what we covered in the first 4 chapters of this course, and rotation, the material that's in the 2 chapters we're working on currently. This diagram, taken from the end of Chapter 9, is meant to illustrate the fact that when you've got an extended object that might rotate or translate, it's the center of mass of that object that follows the trajectory of a point particle that we analyzed in, say, Chapter 3. Here I've broken it down and removed all the other stuff so you can focus on the object. The red little target thing indicates the center of mass of the object. And you'll notice it's at about the center, which means those 3 objects have the same mass. We might have to imagine that the 2 small ones are steel and the larger one is wooden, and the larger one is being used to make it easy to see how the object rotates as it moves. This object is tumbling as it's been thrown, so the next picture shows it having risen to a higher point on its parabolic trajectory and also rotating. And as it continues in its motion, it rotates some more and some more. The motion of the center of mass, the translation of the center of mass, is what we analyze when we use translational kinematics, the material in, say, Chapter 3 for 2-dimensional motion, like we see here. The rotation around the center of mass is what we're currently studying. It's described by rotational kinematics of the object relative to some coordinate system that's fixed relative to that center of mass. That motion is described by variables that are typically angles and derivatives of angles that use Greek letters. So familiar theta, omega, and alpha. You probably know theta as an angle, and that's why we use it as an angular position here. Its units should be in radians, that's its standard SI unit, but you can also use degrees or revolutions or even gradients. I want to remind you that the angle theta is positive when you have a counterclockwise rotation. That is the standard definition that we use both in mathematics and in physics. The next symbol is omega. The first thing I want to impress upon you is that you should learn this symbol as omega. Don't ever call it W. If you hear another student calling it W, please correct them. You don't want to sound like you came from a second-rate university when you're learning, when you talk to someone else about this kind of material that you're learning right now. So that symbol is omega. It's quite different from capital W or lowercase w, which represents things like work or weight. So omega is the derivative of the position, so it's the angular velocity. Its units are radians per second, but you also will see RPM, revolutions per minute, in a lot of applications. Alpha is probably familiar to you. It's the first letter in the Greek alphabet, and as such it's the same as A, and that's why alpha is used for the angular acceleration. We just replace A with alpha. That's a pretty easy thing to recognize and learn, and of course it's the derivative of the angular velocity and therefore the second derivative of the position. Its units are radians per second squared. Now, although other units are possible here, you could do problems in degrees per minute, for example, degrees per minute squared. Alpha must be in radians per second squared when it's used with torque. Now, there's 4 equations for rotational motion with constant acceleration. You want to learn them by analogy to the linear ones in the same order. The 2 that are the velocity and position equations, and the 2 that are the timeless equation, which is the velocity squared equation, and the one that's the average velocity equation. You also need to understand the angular units and variables that appear that are unique to this kind of motion. So let's look at them in turn. The angular velocity equation for constant angular acceleration alpha is omega final equals omega initial plus alpha t, where omega is, as I said, the derivative of the angular position, and omega naught is, of course, the notation for omega at t equals 0, the initial velocity. You notice that it looks exactly like the equation you already know for v equals v naught plus at that we use for constant linear acceleration, or for that matter for 2-dimensional motion, when those all become vectors. Notice that you just replace v with omega and a with alpha, and in fact, in an initial course like this, I'll even tolerate you using that equation with angular variables just so you don't make mistakes. the angular position equation is analogous to x equals x naught plus v naught t plus 1/2 at squared. It says the final position theta is equal to the initial theta plus omega naught t plus 1/2 alpha t squared, where again theta is the angular position as a function of time, omega naught's the initial position as an angle, and omega naught is the initial angular velocity. The third equation, the timeless one, the one that has time eliminated, is omega final squared equals omega initial squared plus 2 alpha delta theta, which I sometimes write as omega 2 squared minus omega 1 squared equals 2 alpha delta theta, which of course again looks exactly like the corresponding equation that we use for many, many problems in our 1- and 2-dimensional problems, but in particular also recognized as being related to conservation of energy, and that is also true here. Then we have the average velocity equation, the one that actually defines average velocity. The standard equation, theta equals theta naught plus omega average t, that is true for any conditions, but when the acceleration is constant, we can replace omega average with the arithmetic mean, that is the average of the initial and final angular velocities. Again, this is exactly like the fourth kinematic equation as I normally list them in class. So you should know them in this order, changing linear variables into angular ones as necessary, and use them just like we use the linear kinematic equations. Problem interpretation is the same. We'll use the known and unknown approach, but we have to sometimes be a little bit more careful about our units. Before I go to units, there's another similarity between the things that we do in translation and what we're learning to do in rotation. We get the rotational acceleration in radians per second squared from an equation that relates alpha to the net torque. That's the Greek letter tau there for torque, which is a twist, divided by I, which is the rotational inertia, what's called the moment of inertia. And here the twist causes the rotation, and I, the inertia, resists it and therefore limits the rate of angular acceleration in exactly the same way that force causes a linear acceleration and the inertia, the mass, limits how big that acceleration can be. One thing you should do, if you haven't done so already, is make up a list of the equations you've been using so far in this course. It's become a little bit longer at this point, and you should, just by writing them down, help reinforce what you've learned about those formulas that we use a lot. But if you write them up in parallel like I've done here, linear on the left, angular on the right, you can see the structure of the problem, as I've already shown you on these first few slides. But there's a lot more to it than what I've talked about here. And some of those are shown at the bottom of this page, and even more at the bottom of this page. Now, you don't need to spend a lot of time copying this down because I've made the PDF that's basically a scan of my own notes available to you in this course. Now, finally, units. The radian is kind of a funny creature. It's not really a unit like meters or degrees, and as a result, it can come and go in equations in ways that can seem mysterious. The reason is, what the radian indicates is that our angular quantity has been measured as a dimensionless real number. It tells the reader that the number is an angle rather than just a plain old number. The reason is it comes from the arc length formula. S equals r theta is only valid when theta is in radians. And in fact, it also defines the angle theta as S over r. In fact, radians means real number because when you measure that angle by S over r, it comes out to be a pure real number. You divide S in meters by r in meters, and the units cancel, so we just have a plain old number left over. What we're doing when we use radian is we're using that unit to indicate that we didn't forget to write down units. Rather, we are intentionally writing down radians so no one will guess that we forgot and actually meant to mean degrees, radians, or grads. So it's really a placeholder to mean that we are measuring our angle as a real number rather than in something that actually has units, like degrees. The relationship is probably familiar to you. 1 revolution is 360 degrees, is 2 pi radians. And my main comment, like I've already said earlier, is that when in doubt, convert to radians. If you've got a problem where everything is in degrees and seconds, you can leave it all in degrees and seconds. But if you got a mix of units, convert to radians. And in particular, if you're going to use the answer like alpha in an equation like torque equals I alpha, or if you're going to use the angle or the angular velocity in something like s equals r theta or v equals omega r, those angular variables must be in radians for that equation to be valid. And finally, just as a reminder, do you know what your calculator does when you use it to evaluate sine of x? Well, when your calculator is in radian mode, it just feeds your input number into its sine function and displays the answer because your input's a real number and its sine function works on real numbers. But when the calculator is in degree mode, it quietly behind the scenes converts your input into a real number by multiplying it by pi over 180. So now it's a real number in radians if you like, and then feeds that real number into its sine function. So again, as before, some of these, one particular figure was taken from chapter 9 of our textbook, although heavily modified for what I've shown here.